Hello student, in the last lecture we have seen that examples in question number 3, 4 and 5 in exercise 8.1. Now we will take example in question number 6. So the question number 6, identify discontinuities for the following functions as either a jump or a removable discontinuity. Here we have to identify the given function is either a jump or either a jump discontinuity or a removable discontinuity. So the first example, function f of x equal to x square minus 10x plus 21 upon x minus 7. So the given function f of x is equal to x square minus 10x plus 21 divided by x minus 7 is a rational function. And it is continuous for all x belongs to R except at those points whose denominator is 0, except when x minus 7 equal to 0, that is x equal to 7. So this function is continuous for all x belongs to R except its denominator is 0, means at denominator is 0, at x minus 7 is 0, means at x equal to 7 it is a discontinuous. And so therefore f of 7 is not defined. F of 7, function of that point is not defined because it is discontinuous here, is not defined. F of 7 is not defined, so that function f is discontinuous at x equal to 7. And so we check the function whether this limit of this function is exist or not at x equal to 7. Limit of function f of x as x tends to 7 is equal to limit of x square minus 10x plus 21 divided by x minus 7, limit as x tends to 7. So we find the limit. We apply limit to this function on both sides as interval x tends to 7. So therefore, actually we take its factor. So factor of this 21 whose sum is minus 10. So 7 3s are 21. So x square minus actually 7 3s are 21. So x minus 7 and other factor is x3 here. So minus 3 minus 7 minus 3, its multiplication is 12 plus 21 and whose sum is minus 10 divided by this x minus 7. And so the common factor will be cancelled here. So it is only limit as x tends to 7, factor is x minus 7. Now we apply limit as x tends to 7. So 7 minus 3, so it is 4. So limit of that function as x tends to 7 is exist. So therefore limit of f of x as x tends to 7 is exist. But f of 7, function of that point is not defined. F of 7 is not defined. And so if we define this function f of 7 is equal to this 4. If we put this function of that point, means f of 7 equal to 4, then the function is continuous. Function will be continuous at x equal to 7, and therefore the given discontinuity has a removable. Discontinuity has a removable. So this type of discontinuity is a removable. Removable type of discontinuity is removable. So now we will take next. Now take second example. Function f of x equal to x square plus 3x minus 2 for the interval x is less than or equal to 4, and function f of x equal to 5x plus 3 for interval x is 4 greater than 4. So we check here. Since this interval is x is less than 4 for this function and x is greater than 4, means we have to apply less than 4, that's why I apply left hand side limit and apply right hand side limit to this function because it is x is greater than 4. So for interval x is less than or equal to 4, the function is equal to x square plus 3x minus 2. So x is less than 4. Apply left hand side limit to this function on both sides. Limit of function f of x as x tends to 4 minus is equal to limit of x square plus 3x minus 2 limit as x tends to 4 minus. So apply limit directly here. So 4 square plus 3 into 4 minus 2. So 4 square is 16 and 3 4s are 12 minus 2. 16 plus 12, it is 28 minus 2. So it is 26. So the left hand side limit of this function is 26. Now we check for this interval. For x is greater than 4, the given function is equal to 5x plus 3. So since x is greater than 4, so we have to apply right hand side limit to this function on both sides. So therefore limit of f of x as x tends to 4 plus is equal to limit of function 5x plus 3 as x tends to 4 plus. Apply limit directly here, and so therefore here 5 into 4 plus 3, 5 4s are 20 plus 3, it is 23, and so therefore right hand side limit of this function is 23 and left hand side limit is 26. So from 1 and 2, equation 1 and 2, we get left hand side limit of this function is not equal to right hand side limit of the given function, and so limit does not exist, it's common limit. Common limit of the function is f of x as x tends to 4 only, does not exist, and therefore f is discontinuous. f is function f is jump discontinuity. f is a jump discontinuity. Remaining examples, example number 3 and 4, you may try to solve at home. Now we will take next question, question number 7. So the next question, question number 7, show that the following functions have continuous extension to the point where function f of x is not defined. Also find the extension here. The first example, function f of x equal to 1 minus cos 2x upon sin x for x is not equal to 0. So given function f of x equal to 1 minus cos 2x divided by sin x for x is not equal to 0. Therefore, it means that f of 0 is not defined. f of 0 is not defined. And so therefore, we check this limit. We find the limit of the function as x tends to 0. So continuity. Limit of f of x as x tends to 0 is equal to limit of 1 minus cos 2x divided by sin x as x tends to 0. Check the limit. So here by using double angle formula, 1 minus cos 2 theta is equal to 2 sin square theta. So therefore we write this 2 sin square x here divided by sin x by using double angle formula. Since 1 minus cos 2 theta equal to 2 sin square theta. So this sin square x and this sin x will cancel. So remaining only 2 sin x as x tends to 0. Apply limit as x tends to 0. So 2 into sin 0. 2 into sin 0. Sin 0 0. So 2 into 0, it is 0. So limit of that function as x tends to 0 is equal to 0. And therefore, if we define f of 0 equal to 0, function of that point equal to 0, and so therefore function f will be continuous at x equal to 0. If we put function of that point equal to 0, then the given function is continuous at x equal to 0. So f of 0. So therefore, continuous extension is equal to 0. Continuous extension is 0. So that is f of 0 equal to 0. Hence we find the extension here, continuous extension, f of 0 equal to 0. So the example number second and third, which is same as to example number first. That's why you may try to solve at home. Now the next question, discuss the continuity of the following functions at the points indicated against them here. The first example, function f of x equal to root 3 minus tan x upon pi minus 3x for the interval x is non pi by 3, and for x equal to pi by 3 the given function, the value of the given function is 3 by 4. So we check this continuity here. So given f of pi by 3, f of pi by 3 is 3 by 4, call equation 1. Now we apply limit as x tends to pi by 3 to this function on both sides. Limit of function as x tends to pi by 3 is equal to limit of root 3 minus tan x divided by pi minus 3x, limit as x tends to pi by 3. Okay, now here interval is x tends to pi by 3, x tends to pi by 3, that's why we put here this interval plus h here, put x equal to pi by 3 plus h, and whenever put there, then interval is changes here. So as x tends to pi by 3, interval x tends to pi by 3, then also s tends to 0 here. S tends to 0. Whenever we put this interval plus h, then interval will be changes. So therefore our limit changes here, interval change in this side only, this side is as it is here. Limit as x tends to pi by 3 is equal to function f of x is equal to limit as h tends to 0, it is root 3 minus tan x, tan of pi by 3 plus h divided by pi minus 3 into pi by 3 plus h. Okay, so therefore is equal to limit as h tends to 0, root 3 as it is minus tan of a plus b. Tan of a plus b is tan a plus tan b divided by 1 minus tan a into tan b. Whole divided by pi minus, when we multiply this 3 to these two terms, so 3 into 3, 3 will get cancelled, it is minus pi, and plus into minus, it is minus 3 into h, it is minus 3h, plus pi minus pi will get cancelled here. Now we multiply here, cross multiplication, root 3 to this total terms, but we know that value of tan pi by 3 is root 3, it is root 3, so therefore it is equal to limit as it tends to 0, so multiply this root 3 into 1. So first of all, root 3 minus the value of this tan pi by 3 is root 3, and so plus tan h, yes, divided by 1 minus root 3 tan h here, and whole divided by minus 3h only. Now cross multiplication here, h tends to 0, 1 into root 3, it is root 3, then root 3 into root 3, it is 3 tan h, and then minus this root 3 and minus into plus minus 3, it is a minus tan h only here, tan h divided by this minus 3h into 1 minus root 3 tan h, and so therefore it is equal to, so plus root 3 and minus root 3 will get cancelled, so minus 3 tan h minus tan h is minus 4 tan h, minus 4 tan h divided by minus 3h into 1 upon 1 minus root 3 tan h. Okay, now apply limit. So this minus minus will get plus. 4 by 3 is constant, take before the limit. Limit as h tends to 0, tan h upon h into 1 upon, apply limit separately, as h tends to 0, 1 minus root 3 tan h. So therefore it is 4 by 3 into limit of this tan h upon h, it is 1 into 1 upon, here when we apply limit as h tends to 0, this tan 0 0 0 into root 3, it is 0, so it is only 1 by 1. So therefore 1 into 1 by 1, it is 1 by 1, 4 into, so it is 4 by 3. So this is the limit of that function. Limit of f of x as x tends to pi by 3 is the value of this limit. Call this second equation. Now from first and second, it is 4 by 3, it is 3 by 4 from first and second. From first and second, so right hand sides are not equal, therefore left hand sides are also not equal, is not equal to function of that point. Limit of that function is not equal to function of that point, therefore f is discontinuous. Function f is discontinuous at x equal to pi by 3. Hence we discuss the given function is discontinuous at x equal to pi by 3, and the remaining two example number second and third, you may try to solve at home because it is same as example number first. So today we will stop here.